I first want to thank you for coming at this time of post-meal nap, for hearing mildly discomforting things. And also, I want to thank Françoise, Jacques, and Emmanuel for a number of slides I stole from them shamelessly. Okay, so the subject is, well, you all know the subject. We're confronted to a possible collapse. And that's a subject that has become fashionable in the last few years due to the book, in France at least, due to the book of Servin and Stephens. It's something that have been part of our preoccupations in the STEEP team for a number of years, and it has kind of renewed our activity on that. And the sub-question is, what does the digital technologies have to do with that? Okay. So I'm going to justify, or in as much as possible justify, why we are on a collapse path. And for that, I'm going to rely on the analysis of limits to growth, the qualitative analysis. I'm not going to delve into the model they built. Actually, it's unnecessary these days. Just the qualitative analysis is sufficient to understand why we are on the collapse path. Okay, so ideas from that. I'm speaking here of environmental collapse. There are other types of collapses I'm going to briefly touch upon during the course of the talk, but mostly I'm talking about global environmental collapse here. In this type of analysis and drawing on ideas from population dynamics, they just pointed out that you only need 4 conditions to be satisfied in order to have collapse. And these 4 conditions apply to the interrelation between a population dynamics and a biocapacity that sustains this population. The 4 conditions are written above here. One is you need your population to grow. You need your population to overshoot your biocapacity at some point. This is time, this is population and biocapacity. This is population, this is biocapacity. This is, roughly speaking, where we are nowadays. We're above biocapacity already. What does that mean? It means that we're using renewable resources faster than they renew themselves. So obviously it can't last forever. And you have 2 possibilities. Either you have some kind of mild landing getting you back to your biocapacity, or you erode your biocapacity while you're in overshoot and erode it so much that the population can only reach back to the biocapacity in a catastrophic way. And that can take a long time. But that's really the issue, because we're already here. And the 2 conditions making the difference between the 2 options here are the amplitude of your reaction delay and the amplitude of your erosion of environmental biocapacity while you're in overshoot. Okay, so I'm going to show you why all these conditions are already satisfied. This is why we are on a global collapse path. Okay, physical growth of population and its demand. That's world population from the beginnings of the Neolithics. That's beginning of agriculture about 10,000 years ago. And there is a high peak starting at the turn of the 20th century, basically, in which we very fast increase population by billions. This peak of population has been associated with a dramatic increase in all types of demands and pressures on the environment, demands in terms of energy, demands in terms of metals, demands in terms of meat, demands, and that's per capita, demands in terms of agricultural products, cereals here. They all inflated in the last 50 years. And these last 50 years have been called, because of that, the Great Acceleration. Okay, so that's for growth. Everyone knows we are growing, that our demands are growing, etc., etc. What about overshoot? I think the most popular measure of overshoot is the ecological footprint. So this is some kind of a compound indicator that brings together a number of very different things. It's a measure of the surface you need to satisfy your current needs. The surface you need in terms of built areas, the surface you need in terms of forest. We need forests for paper, for example, or for construction material, or also for just for energy. Of course, for agriculture and cattle raising, and it also includes some fisheries and things like that. So it's a kind of strange compound indicator. Some of the choices that were made in order to bring all that together are kind of conventional, so it's kind of debatable. But still, the global trend is quite firm. And also, I want to point out that this indicator ignores a number of impacts we have on the environment. Mostly, it ignores all sorts of pollution. Okay, so what's the trend? The trend is that, and it's divided in a number of sectors. The most important one is carbon emissions, greenhouse gases emission mostly, but in terms of carbon we reject into the atmosphere, and then what we need in order to put that back into the soil. That's the surface you would need, equivalent surface you would need to do that. The second most important thing is this one. It's cropland, it's agriculture. The fastest growing is carbon. The second fastest growing is cropland in terms of impact. That's world biocapacity. And we crossed it somewhere in the 70s, and now we're somewhere 50% above threshold. You can see two diminishing tendencies. This is the first oil shock, this is the second oil shock, and that's the 2008 crisis. Needless to say, it doesn't last long. We always go back to the global trend. Actually, we're already back to increasing the carbon emissions. Okay, there is one thing here. It's highly inhomogeneously distributed in terms of countries. Of course, the highest impact is due to developed countries, by far. God. Hey, why doesn't it want to go back? Okay, sure. Here it is. The second measure of overshoot has been devised a few years back, around 2015, first paper, 2018, second paper. It's called Planetary Boundaries. They have been immensely successful, these two papers. The concept has been immensely successful. So these people, quite a lot of people actually, pointed out that there are at least 9 critical sectors which we have to be careful about in terms of threshold, or at least limit. These 9 sectors include climate change. They measure that with greenhouse gas emissions. Naval entities is basically all sorts of pollution. Stratospheric ozone depletion, the ozone layer hole, atmospheric aerosol loading, and aerosols are important for health issues, but also for cloud formation. Ocean acidification, biochemical flows, and the two they mention are the ones connected to agriculture. Phosphorus and nitrogen. Agriculture just explodes the natural cycles of these elements, and the man-made cycle is now dominating the natural one of these. Freshwater use, land system change, that land use. Agriculture is the major factor driving land use, and biodiversity integrity, both in terms of number of God, I'm looking for the word even in French. Okay, the size of a species and the number of species. The one on the size of species is much better known than on the number of species. So many species are not known that we have very little understanding of that. We know maybe 1/10 or 100 of all species on Earth. Okay, we explode the limits on at least 4 or 5 of these boundaries. Also, they interact with each other. As I said, for example, land use change is the major driver. No, I didn't say it. I'm saying it right now. Is the major driver of loss of biodiversity, et cetera, et cetera. They all interact with one another, so you can't act in a sectorial way. You need to act on all fronts at the same time. So I mentioned the ones which are exceeded, the ones that are need to critical, et cetera, et cetera. We are exceeding at least, for sure, 3. Okay. Okay. That was for overshoot. Now for erosion of biocapacity. We are eroding biocapacity on quite a number of fronts. One is, of course, biodiversity loss. I just said that agriculture is the major source of biodiversity loss. The second source is climate change. How can climate change create biodiversity loss? There are many processes. One, for example, in France, species are moving up north due to climate change, but they don't move at the same rate. So you have species which were belonging to the same ecosystem that start to belonging to different ecosystems, and they are not adapted to that, and that perturbs them significantly, even to the point of extinction, for example. Another effect is, for example, bird hatching no longer occurs at the same time as the larvae maturation. So birds no longer have food at the right time. Even a 2-week time difference between the two is sufficient to produce a large perturbation in some sorts of species. So you have a lot of impacts of that kind of climate change over biodiversity. The reason why agriculture is the major source of loss of biodiversity is obvious. If you look at these vast plains devoted to agriculture, there is absolutely no room for anything else. Okay, so we are now, due to these factors, in a situation where the rate of biodiversity loss is about 100 times faster than the natural rate, and it's expected to be another 100 times faster in the future. So we are facing a massive extinction of species on a time scale which has never been seen in the planet. The last extinction was the dinosaurs. That was 65 million years ago, and it took a long time. We're doing this in just a couple of hundred years, not millennia, not millions of years. Okay, second point of erosion of biocapacity. I didn't ask, how much time do I have? Sorry? Oh, so I removed too many slides from the talk. I expected 45 minutes, and I had a budget talk initially, so I removed quite a lot. Okay, so second point of erosion of biocapacity, soil erosion. Agriculture is the major soil occupation worldwide. That's what was shown here. What's not agriculture here is tropical forests, some here, deserts, of course, etc. But basically, this is not only agriculture. This is, well, yeah, this one is only agriculture. The other one is both agriculture and grazing land. Basically, everything but tropical forests, remaining tropical forests that can be put to use for agriculture has been put to use for agriculture. The problem with that is part of it is being eroded from mild to severe erosion. That's a map of erosion due to agriculture, soil erosion due to agriculture. About 1/2 of the surface that is in, well, I have to be careful about that, that is in use for agriculture these days has been put in use in the 20th century. At the same time, about 40% of what is actually in use nowadays has been degraded by agriculture. And if you look at the evolution of that, you see that about as much soil is put out of agriculture as is put into use. And so basically over the last 50 years, the overall surface that is cultivated has not changed, but part of it has been removed because it's too eroded or even desertified. And the rest has come from logging of forests, especially tropical forests, to put that into use for agriculture. Okay, so we have degraded about 40% of that in the 20th century. We have put into unproductive use more than what is cultivated nowadays over the last millennium. So we have a way of doing agriculture that is extremely damaging. We absolutely need to change that. We can't go on with that. There is not enough room to go on doing this for forever, not even forever, just for decades. We just can't go on doing this even for decades. By the end of the century, we'll need to have changed that. Extreme erosion leads to desertification. Once you have completely destroyed your topsoil and the vegetation cover that maintains its coherence, the only thing that can happen is the soil is removed until you reach the bare rock. Before that, nothing can stop it. About 20% of continental surfaces are in a desertification process these days. And that's a threat for over 1 billion people. That's a lot of people. That's about as many people as lived on the planet at the beginning of the 20th century. It's a lot of people. And also, desert progression is accelerating. It's nowadays twice as fast as it used to be in the 60s, for example. So, we are not only eroding soils, but we are destroying them. And can we go on with producing what we produce nowadays? We can still log. We can still log this and this mostly, and turn that into productive use in terms of agriculture. The problem with doing that, we can also log some temperate forests that are not primary, but anyway, it's the same basic problem. The problem with logging the tropical ones is that they have a big role in terms of climate change mitigation. They have a big role in terms of how to say that, precipitation regulation, for example. If you have questions, I'm going to explain the process later on, but not right now. So if you suppress all tropical forests, you actually degrade the problem of climate change in a very, very significant way. It's certainly not a good idea to do that. Okay, so as I have a little more time, I'm going to go back to some of the view graphs I have suppressed. Third area of concern in terms of erosion of capacity is hydrological stress. Hydrological stress is what happens when you remove too much of fresh water with respect to the resource. Fresh water comes in rivers, in lakes, in aquifers, shallow depth aquifers, but also deep fossil aquifers. Deep aquifers means kilometer depth, like petroleum exploration, for example. And it's fossil because it cannot get replenished over any significant time scale for us. It takes millions of years to replenish such deep aquifers. So once you have just emptied it, it's a one-shot pistol. It's different from the shallow depth ones, which are replenished on a yearly basis. Okay, so this shows places where withdrawals exceed what is reasonable in terms of replenishment of the resource, and also in terms of ecosystems. Ecosystems also need they also need, what did I want to say? Yes, they also need, every living thing needs water. Okay, so where does withdrawal come from? It comes from three sources. Agriculture, about 70% of freshwater use is for irrigation worldwide. About 20% is for industry. About 10% is for domestic use. So what? This first, well, yeah, let me comment on that one. This is one of the main agriculture producing regions. There is also one here very important for in the south of Chicago, very important for cereals like wheat, for example. But there is a gigantic fossil aquifer here about that size that's being depleted extremely fast. It's already depleted in some places. That means we have reached the bottom in some places. And the bottom is not flat, but kind of corrugated. There are places where there is still water. So in the States, they've stopped irrigating in places because they've already reached the bottom of this gigantic fossil aquifer. It's not surprising here. These are semi-desertic areas. Here is the North Plains of China, which are the most producing plains for China. So they also have a problem of water overuse. And all of India is in severe hydrological stress. That's billions and billions of people that are threatened by lack of water in a term of a few decades at most. If you add these, that's about 2 to 3 billion people. Another problem with hydrological stress, is there a clock somewhere in the room? Oh yeah, it's here. It was just, okay, sorry. Is the melting of glaciers worldwide. In the Andes, in the Himalayas, that's the Himalaya region here, but in Europe as well. I don't know if any of you have gone to see the Mer de Glace. It has been receding absolutely dramatically in the last couple of decades, basically. But this is happening worldwide. The most threatened glaciers are the Andes ones. Many cities in the Andes, a city like La Paz, for example, in Bolivia, if I am not mistaken, lives only due to the water due to glaciers. No glacier, no water. Agriculture needs glaciers for irrigation in summer. Why? Because you take most of the irrigation water from streams, from rivers. And these, in summer, have their water coming from glaciers. If you remove glaciers, you have no longer any stream or river in summer. This one is particularly worrying because all the great rivers of China have their springs in the Himalayas, and it's the same for a large part of the rivers in India. So as soon as these are gone, about 2 billion people, well, almost 3 now, are going to run out of irrigation water during summer. That's where you mostly need it for crops. And that's a result of climate change, of course. So fresh water is a critical resource that's soon going to be a problem, and it's true in Europe as well. The major rivers in Europe, le Rhône, le Rhin, etc., have their origin in the Alps. The disappearance of the glaciers of the Alps is going to imply that we also won't be able to irrigate during summer. Hey, well, oh no, I know. I have to go back to where I was. Okay, so in terms of erosion of biocapacity, I've pointed out 3 factors. One was biodiversity loss, the other one was erosion and desertification, and the last one was freshwater availability. These are the major threats for the coming century in terms of erosion of biocapacity. Okay, now reaction delay. There are so many causes of reaction delay that I will only be able to discuss a few of them. So I remind you I'm going through all the 4 conditions that are necessary for population collapse to happen. And that's the last of the 4, reaction delay. There are many, many causes of reaction delay of all sorts that I have basically pointed out here. I want to point out particularly out of these 3. There are competition dynamics that lead to reaction delays both at the individual, multinational corporations, and state level. Individuals compete, well, they collaborate too and cooperate too, but we're in a competitive society more than a collaborating one nowadays. I'm not saying that it's going to be like that forever. It can't be like that forever, but nowadays there is an excess competition over collaboration. People compete in terms of mimetic effects. They want to do the same thing as the neighbors, and especially the neighbors a bit better off than them. And also, there is an interaction between that and unlimited desires. Corporations are in economic competition, everyone knows that, and that obliges them to always do more than they have been doing before, otherwise they die. States are in geopolitical competition. Everyone can see that nowadays. China is trying to grab resources worldwide. The states are trying to react to that. And somehow Europe is a bit complacent with that, but I don't think it's going to last very long. There is a huge worldwide geopolitical competition for resource grabbing. And more importantly, maybe, all this is a consequence of the fact that growth is the cost of maintenance of society, and I'm going to explain why. One important aspect of this last question, that growth is the cost of maintenance of society, is due to an interesting analysis by Joseph Tainter. Joseph Tainter is an archaeologist, and he published a very famous book in the late 80s, and actually worked all his life on that, trying to explain some kind of meta-explanation of civilization collapse by looking at the interplay between complexity and efficiency of problem solving in a society. When you're in a relatively initial state, not so much complexity, not so much efficiency, you have a lot of gain of efficiency by increasing complexity. The problem is that after some point, you reach diminishing returns. You increase complexity, but you are less and less efficient. And the problem also is that once you're here, you're in this type of lock-in. The only thing you can do to tackle problems is increase complexity, because you're already too complex to do anything else. Okay, so what does this mean with respect to what I said earlier? Complexity is a hidden energy demand cost. You cannot increase complexity without increasing energy demand at the same time. So this is one of the main sources of the growth of impacts on biocapacity. You need this energy because you need to extract more materials to maintain an increasing level of complexity of your society. And the loss of efficiency in this second half of the evolution is a direct source of increased reaction delays. Just the fact that we need, for example, we've been discussing climate change abatement with international meetings after international meeting for 40 years, and that's resulted in absolutely nothing. Greenhouse gas emissions have just not only increased but accelerated. The emissions have been accelerating while we were having these discussions for the last 40 years. And it's the result of increased complexity in last analysis. Okay, so what does complexity mean a little bit? You have two sorts of complexity in Tainter's view. The first he calls horizontal complexity. It's the specialization of activities in a horizontal way. For example, I have an example here for the build and use of smartphones. Everything you need to make a smartphone comes from everywhere in the world. That's true for everything. If you want to build a plane these days, you need resources, work, etc., from all over the world. ITCs, no, ICTs, are a major example of this complexity, this type of complexity. It's effectively very difficult to track where components come from in the end. So that's horizontal complexity. This one is vertical complexity, that is complexity in terms of organizations, structures and institutions piled one on top of the other. And that's an example of the French higher education landscape. Those who are old enough, like me, in the room remember a blessed time where it was so much more simpler that we just don't know how we came out to that. Okay, now the connection between complexity and energy use. A measure of complexity of activity, increase of complexity of activity is the world gross product. It just measures activity. If you increase it, you also measure through that the increase of complexity of your activity. And energy use is here. And there is an exact correlation between energy and world GDP. So that tells you, by the way, that decoupling cannot occur. When you hear things that, well, in Europe we're starting to decouple activity from energy use, that's because we put energy use elsewhere in the world. Worldwide, there is no decoupling, and there can be no decoupling. So energy is what you need to the first level to maintain your increased complexity of activity, and then all the rest comes from it. The number of metals you extract, the size of your agriculture, the fact that it's highly mechanized, etc., highly impacting. All that comes from energy, and all that comes, in the end, from increase of complexity of societies. So we're facing some kind of a conundrum here. There is extremely little chance when you see this, and when you see this, that we will ever voluntarily reduce our increase of material and energy use, our growth of complexity, our reaction delays, which partly and actually largely come from increase in complexity, and all sorts of environmental impacts that are associated to it. So you're stuck with increasing reaction delays and going on eroding biocapacity. And as time goes on, we're moving away extremely fast from that into this. And nowadays, it's almost impossible to avoid this. So the question is what we do about it, but there is a second part of the talk. First, I'm about right. About what the role of, and I also made a mistake here, the role of ICTs in all this mess. Okay, the short answer is it's a problem and not a solution. And the question is why? The first big why is that by far the role of numerics in all this is that it's a boost of the great acceleration. It helps complexifying, accelerating things, making things more dependent and complex all the time. Because of that, it accelerates all sorts of material flows, production processes, obsolescence, etc., etc. So it just impacts in the wrong way on what we would like to do, that is kind of decelerating that. As you can see, telecommunications have exploded from 80s, 90s, which is not surprising. It's due to the explosion of internet. Transportation, which is a measure of physical exchanges, goes the same tendency over a longer time scale. And there is no dematerialization behind that. I mean, if you increase communication, at the same time you increase people and goods transport. And that is an impact. Here is shown two of the associated impacts on ecosystems. But in the publications I mentioned earlier, called exactly that, the great acceleration, there is a whole host of these things that are all growing at the same time. So numerics is a booster of that. That's the first major effect. By far, anything else is lost in that. That doesn't mean that direct effects are, no, sorry. I have so many things to say about indirect impacts that I need to go on for that for a while. There has been a talk given on this topic by Françoise, who is in the audience. And you can see it on the YouTube channel of the team called Comprendre et Agir. So she gives a lot more information than I'm going to do about it. And in fact, what I'm saying here comes from what she says about that. Okay, so an important aspect of this amplification mechanism of numerics is its effect of amplification on rebound effects. Rebound effects abound in a forced growth system. We're in a forced growth system, as I explained to you earlier, due to this complexity increase lock-in. In a forced growth system, all gains in terms of efficiency per unit of anything translate in the end in an increased global use of the same thing. Whatever you do, you always end up like that. Why? And the why can be understood on this example of about carpooling, long-distance carpooling. The idea is kind of simple. If you have two people wanting to go from one place to another, each using a 1-ton car to move about 80 kilos of flesh, it's highly inefficient. It's better to put two 80 kilos people in a 1-ton car, and that's going to be some kind of improvement in terms of energy use. Well, moving 2 tons instead of 1 is obviously a gain in energy use. That's an efficiency gain. That's the idea behind carpooling. The problem is that you have all sorts of consequences to that. The first thing when you gain efficiency is, well, the first thing, most common thing, is you also reduce costs. And when you reduce costs, you increase the population basis that can access the service. And you increase this more than you increase your efficiency. So that's the first thing. You're going to increase the demand of car travels of this type. There is a substitution effect too, that reducing the cost makes it more attractive to use a car than to use trains, for example. But the problem is a car has a much larger impact in terms of greenhouse gas emissions than train. So just because of that, you increase the demand of this type of thing. And in the end, you produce more greenhouse gas emissions that you expected to save just by carpooling. It's typical of all kinds of rebound effect. And rebound effects abound in our society. They are everywhere. There are indirect effects also associated with that. That is, the gas you have saved individually, you can invest elsewhere. For example, to go at the end of the world for your vacation, and then you explode your carbon budget for the year. I don't want anyone to feel bad about it. Sometimes I do exactly the same thing, so don't worry. Okay, so without numerics, without internet, you can't do that. You can't coordinate people to carpooling. And it's true of all sorts of things. Numerics doesn't produce rebound effect. Of course, it's our forced growth society that produces that. But numerics amplifies it by all sorts of means. That's just one example. Okay, now to direct impacts. I think I'm still good on time. Okay, it speaks by itself, I guess, if you can read what this is about. That's energy demand increase due to all sorts of numeric digital devices. That's the metal type and quantity increase. Most of it recently is rare earths and heavy metals, and that has to do a lot with ICTs. Of course, these are only byproducts of the production of more structural metals, but still. That's the number of devices over the years. That's the number of connected devices over the years. Everything explodes. So even though direct impacts are much less important than indirect impacts of digital technologies, they are not negligible. They are not dominant, but not negligible. So that's the pressure. What are the actual impacts associated to that? Well, you have two kinds of impacts, some associated to mining, some associated to end-of-life pollution. Mining impacts are, of course, localized, but some are diffusing, localized to the mine site. Some mines are gigantic, 1 kilometer wide, 1 kilometer deep. And there are many of them in the world in use. One of the first impact is water overuse. You need a lot of water for many mining processes. You also produce a lot of pollution. For example, for gold, you need cyanides to extract gold, and these just stand in the environment after that. They are never cleaned, they are never removed. They just stay where they are. They diffuse in the soil, they diffuse in the water. And this type of diffusion in the soil doesn't go very far, but in the water it can go very, very far. There are issues of toxicity, of course, associated to that. End-of-life pollution is a bit similar. When you try to recycle what you can recycle out of these things, you use persistent organic pollutants, all sorts of chemical compounds, and also whatever you do, some heavy metals end up in nature, and heavy metals are a big source of toxicity for ecosystems and humans alike. Okay, so this is the list of impacts associated to that, but I'm not going to comment much more on that. I think I still reduced it too much, but it's all right. That will leave more time for questions. Okay. Last point, reaction delay. That's a view graph I stole from Emmanuel. The first is illusion of dematerialization. That's what's sold to you. If you see a landfill of computer refuse, it's absolutely awful. It has nothing to do with that. If you see how people in developing countries manage to try to get what they can out of that, they do that in terrible health conditions. So reality has nothing to do with that, but that's what we are sold, and especially that the thing, the mess is put elsewhere. We don't see it. Because of that, actually, we're also blind to the back reactions I just mentioned to some extent, that is indirect impacts and rebound effect. We just don't see that, we see that. Well, this is extremely clean, of course. The fact that there is blood in it is not obvious from just looking at it. And of course, we are at best naive, at worst cynical about the complexity, hidden costs, not only the environmental ones, but the human ones. And that kind of blindedness on all three fronts does not give an incentive to react to what's happening. I'm going to give you an example. even by extending it. But with 3 slides, I'm still short of by 10 minutes about. An example of something you probably never thought of an unintended effect of the use of very specific algorithm for high-frequency trading. Everyone knows that, or I hope everyone knows that high-frequency trading in finance is a source of instability of the financial system. But it's a source of other things that are less obvious. And that's extracted from a report from Finance Watch, a very recent one, just a couple of months ago. They point out that if you have a weak but constant trend, for example, a carbon tax that's slowly increasing, the high-frequency trading and actually not only high-frequency trading, but increase of trading pace with more common type of algorithms produces volatility in gas and oil price that extremely easily overwhelms the global trend of your carbon tax, for example. So that's what's happening with 10% volatility. That's what's happening with 60% volatility. I guess nobody is able to see the trend in the signal. As well, maybe if you use a very sophisticated tools, and I'm not even sure. And by sophisticated, I mean more sophisticated than a linear regression, of course. A linear regression will tell you that you don't see the trend behind the volatility. So if you're an investor and need to make, say, a large investment in terms of carbon emission abatement and look at prices, you just decide you do nothing. Unless your carbon tax is so large that it overwhelms the price volatility. But just on the face of this, you just decide to wait and see. Carbon taxes are inefficient after you include into it the problems of price volatility. And the price volatility is a direct consequence of using numerical technologies in finance. Okay. And examples like this abound everywhere. We just don't know about it, but they are everywhere. Okay, so conclusion. First part of the talk, global environmental collapse. Well, collapse is missing. Is on its way and can be stopped. So no use trying to fight that. Better think what you can do, taking that into account. Digital technologies, numerics, is part of the problem much more than it is of the solution. Now, having said that, I point out that numerics helps understand complexity. And that's the major use for me of having a computer that's understanding all these things in a more quantitative way. Because complexity being complex, you can really tackle it with simple means. I want to dispel how can I say that? I don't know. A hoax about the fact that the numerical transition and the ecological transition are going hand in hand. It's absolutely untrue. The numerical transition is aimed at privatizing profits and collectivizing environmental impacts, whereas ecological transition is exactly the contrary. The GAFAM are very well aware of that. And they are some of the major players making numerics a problem and not a solution. Once you see that, you can only think that this view, that the fact that the two, or the idea that the two are connected, is at best naive, at worst cynical. So what can be done? Because things can be done, otherwise I wouldn't be here. I would just do something else, rest, go in the mountain, I don't know, something. Well, first thing, try to stop what is harmful. And that's a very simple thing to say, but a much harder thing to do. First, identifying what is harmful is not that simple. And second, stopping it is even more difficult. But still, you can try to do that. And that applies to research as well. Second thing, you need to evaluate impacts in a systemic way and not just have some time of silo thinking that we are very, very good at. In all domains of society, we're very good at thinking of a problem with, actually we are taught this way in research. We are taught to deal with a problem by segmenting it and then solving a little part of it and ignoring the rest. At the face of what I just said, it's a non-starter. You absolutely need to do things very differently. And last point, but not least, try to imagine alternatives, especially low-tech resilient ones, with or without numerics, but at least try to imagine alternatives. And that's one of the things we're trying to do in the STEEP team. Not that we are very successful at it, but at least we are trying. Okay, I'm done.